So we're gonna pick back up where we left off on Tuesday. So we were talking about finding failures using optimization. And we had set up this optimization problem where we said that we had kind of these variables we needed to decide, which was the initial state and some sequence of disturbances. We were going to minimize some objective function that represents closeness to failure, subject to the fact that tau, or our trajectory, is a rollout given that initial state and sequence of disturbances. So we said we needed some objective that was close, that kind of represented closeness to failure, and we remembered from chapter 3 that robustness does exactly this, exactly what we want here, or smooth robustness if we're going to use an optimization algorithm that needs gradients. And so we said we'll just use this as our objective function. But then we were just talking at the end of lecture about how this might be a problem because it might result in very unlikely trajectories. So if we just tell it to minimize robustness, it can kind of do whatever the heck it wants to try to make it the robustness as small as possible. But in doing that, it could potentially do very unlikely things. So for example, we saw this trajectory here where we're sampling disturbances from our disturbance distribution. But this disturbance here, according to this distribution, is very low probability. It's very unlikely. And if we just do that a whole bunch of times, we are able to make the pendulum fall over. We're able to make the trajectory fail. But this is kind of very unlikely and maybe not the type of failure that we're necessarily interested in. So we said our solution here was going to be to incorporate likelihood into the objective. So that's what we're going to do now. We kind of left off here where we said, okay, well, if we're going to do that, we now need to know how we could actually evaluate the likelihood of a trajectory. So the likelihood of a trajectory is just going to be the likelihood of the initial state that we got, and then the likelihood of all of the disturbances that we sampled after that occurring. So what we're going to do here is we'll show kind of the same trajectory we've been looking at over and over, and now we're just going to kind of keep track of everything that we've sampled and the likelihood of that occurring. So we'll say p tau, we'll say p tau represents the probability of trajectory tau, is going to be equal to the probability of this kind of initial state that we sample. So we look at whatever the probability density was for that initial state. We're going to include that in our probability of the trajectory. And then we need to keep kind of accumulating probability every time we sample something. So next we sample a disturbance for the first time step. So we want to look at the probability density for that disturbance. And now we're saying, okay, it's the probability that this initial state occurred and that this disturbance occurred. And so we're just going to multiply it over here. And then we go to our next state. We now sample another disturbance from this distribution. So we look at the likelihood of that disturbance that we sampled, add that to our product, and then we kind of just continue doing this for the rest of the trajectory, all the way out to our final depth, where we have the final disturbance that we sampled. So the likelihood of a trajectory is just going to be the product of all of these things. So here it is in code. Specifically, we have kind of the product of each disturbance at each time step given the state, action, and observation. We could break that up into each kind of component of the disturbance. So we said we had a disturbance for the agent, a disturbance for the environment, and a disturbance for the sensor. So we just multiply those three together. So that's how kind of each of these breaks down. And so here's what it looks like in code in the book. Here we're implementing the log PDF. We're just taking the log of this. And the reason for that is because as we begin to multiply things, when we multiply small numbers and we multiply many of them together, we get very, very small numbers. And that can be kind of difficult to work with and result in some poor numerical stability. So if we take the log of this, we're able to just do addition instead of multiplication. And so that's why we compute the log PDF here. Here we're also working with logs. So it actually does, this is like only somewhat right, but it actually does return the PDF because we take the exponent of it at the end. But in general, we're working with logs in this function as well, where we're just kind of getting the probability, the log probability for our initial state that occurred, and then we're adding on the log PDF of the disturbance that occurred at every single time step. Okay, so now we know how to calculate the likelihood of a trajectory, so we can incorporate that into our objective function with the hope of finding likely failures. So here's our new objective function that we're going to consider here, and there's two possible cases. So the first case is that the trajectory is a failure. So in this case, it's written tau, not in psi. So every time you see that, we'll use this quite a bit in the class. Anytime you see that, that means like trajectory, not in specification, meaning trajectory doesn't satisfy the specification, meaning the trajectory is a failure. So that's just kind of a mathematical way that we write that a trajectory is a failure trajectory. So if it's a failure trajectory, then we're going to return the negative likelihood of the trajectory. So that means like, if we put a failure trajectory into this objective, we're going to say take that failure trajectory and try to make it more likely, try to minimize the negative likelihood of it. And then the second case here, which is the case at the bottom, if the trajectory is not a failure, then we don't care about its likelihood just yet, we just want to move the trajectory closer to being a failure. So we still try to minimize the robustness if it's not a failure. Okay, so now I'm going to show kind of what this looks like. So here I'm showing a different example than the pendulum we've been seeing. This is a grid world where the agent can kind of move around on these grid squares, but every once in a while, instead of moving in the direction it wants to, it will slip to some other grid square in a different direction. And you can imagine if we had no disturbances at all, so the disturbances here are what causes it to kind of slip in these other directions. If we had no disturbances at all, we would just follow this path here to the goal, and we're trying to avoid the obstacle. And so a likely trajectory is kind of going to stay near this path, but we want it to also fail. So I'm going to show what happens if we just minimize the robustness versus if we minimize kind of this new objective. And what I'm showing here is kind of, what I will be showing is kind of the evolution of a population method, which is kind of a category of optimization algorithms that I'll talk about in a minute. But really the idea is just that we maintain a whole population of samples, so we maintain a whole population of possible trajectories, and our goal is to kind of move that population iteratively towards optimizing our objective. So when I show the next animation here, you're going to see both of these populations change, and you'll see how they differ with one objective versus the other. So let's check that out. Okay, so you can see here, we've kind of converged this population where most of the trajectories just kind of go almost straight to the obstacle. And then over here, we've kind of, with this new objective that incorporates likelihood, we've found this failure that stays kind of close to the nominal path, and then only kind of deviates right at the end and falls into the obstacle. So here's just what that looks like kind of over time throughout the progression of the algorithm. Okay. Okay, so that's what we want to do. And it turns out if we could actually find like the global minimum of this objective, we would get the most likely failure, which is a nice property to have. However, a lot of times we can't actually find the global minimum because our optimization algorithms just aren't designed to do that or aren't able to do that. So I just want to give you a few notes on using this objective. The first thing is that it needs to be the case that failures never have a higher objective value than successes. Because if that's the case, then we might actually not encourage the algorithm to find a failure. It might find a success that's like somehow better than a failure. But you might be thinking, okay, no problem, because when we do have a success trajectory, we know that the robustness is greater than 0. And so we said, you know, in this case where we have a success trajectory, we just return the robustness. So successes are always going to have positive objective values. And then the negative likelihood of something, which is what we return when it's a failure, well, since probability always has to be positive, probability density always has to be positive, this is always going to be negative. So this is always going to be less than 0. So it seems like we're good to go. And that's true. But there's also one more problem, which is that this kind of p of tau here, as we were talking about earlier, we're multiplying lots of things together, lots of small numbers together. So we might get a really, really small number. And this might be not very numerically stable. So it can be difficult for optimization algorithms, especially on the computer, to actually like go about optimizing this type of objective effectively. And so you might think, okay, let's just take the log, which is like what we did before to make everything more numerically stable. But then this breaks our first requirement that the log because the log likelihood could be less than 0. So that means this could be less than 0. So this negative, this could be greater than 0. And then we don't have this property that we needed anymore. And so all of that is kind of just to say that even though if we could get the global minimum of this is what we would want to do. Sometimes a different objective actually works better in practice. And so in practice, what we often do is instead kind of just combine these two into one single case where we say we kind of trade off between minimizing the robustness and minimizing the negative log likelihood. So for example, here we have the robustness, we have the log likelihood, and then we have this weighting parameter that we call lambda, which kind of trades off between the two. So this is a parameter that you would need to tune, and if you kind of looked at what was coming out of your optimization, and maybe you found like, oh, it's not finding failures, then you would want to increase this weighting parameter, et cetera. Or maybe decrease, I don't know. You need to look at like the various trade-offs between the two. Okay, and so then now we have our objective function, and then we need to optimize. So here's the algorithm we provide in the book for it. It looks super simple, because we've kind of extracted away a lot of things here. But really what's going on is we specify some objective function. So that could be anything that we just talked about. So it could be like the robustness, it could be the likelihood objective, etc. We give it some optimizers. So this is really what we're like extracting away quite a bit. But the reason we're doing this is because we've now formulated the problem in such a way that it's set up as an optimization problem. And so there's lots of algorithms off the shelf that people have already implemented that can do this kind of thing for you. And so you could just use open source algorithms to do this. So in the book, we show an example where we use a Julia package for optimization called optim.jl. There's another nice Julia package called jump. There's various optimization packages out there. And you could just kind of plug in an optimizer from any of those that could take in our objective and do this optimization. But I do want to mention a few things about this kind of mysterious optimizer. So we did talk about it a little bit in the lectures on model building. And in those lectures, we kind of just said, it takes in an objective, it takes in some parameters, it does some mysterious stuff, and then it outputs the optimum for us. So I'm going to kind of open up that black box just slightly more, although we're not going to get too in detail today. But what's going on here is now in this case, our parameters that we're inputting to our optimizer are our initial state and our sequence of disturbances. So it gets to pick all of those things. We give it our objective, and then it's going to output kind of this optimal trajectory for us. And there's two different kind of categories of methods that I want you guys to know about. The first category is called local descent methods. And what these methods do is, let's say that this, for example, is our objective function that we want to find the minimum of. A local descent method starts from some initial guess. So here it's just a point. For our actual trajectories, it'll be like a full trajectory as our initial guess. And then it kind of just moves that guess slowly towards a minimum. One kind of very common problem with local descent methods is that it does kind of depend on that initial guess where you end up. So here, looking at this is kind of the global minimum we were shooting for. But if we started over here and we kind of descended from there, we might end up getting stuck in this kind of local minimum. So you're not always guaranteed to get the global minimum there. So one kind of fix to that, or thing that you could try to do to improve, is instead of just taking one sample and kind of moving it towards a minimum, you can maintain a full population of samples and then try to move those towards various minima. So now we're kind of covering more parts of the input space. Okay, and then within local descent methods, there's these things called first order and second order methods. You don't need to know too much about them, but I just want you to know, well, one thing we can name drop a little bit. So gradient descent, many of you have probably heard of. It's very commonly used for training machine learning models. Similarly, ADAM and LBFGS is a common second order method. So those are just a few names, things you might look up if you want to kind of plug in an optimization algorithm. But the real thing I want you to know about these is that they do require gradients. So they require us to be able to take the gradient of our objective function, so for example, the robustness or that likelihood objective, with respect to our inputs. So that means we need to be able to differentiate through like the full rollout function. We need to know all the full model dynamics. We need to know all the mathematics behind it. And so if we have a black box model, like we talked about in the second lecture, this is not going to be plausible because we don't actually know the mathematics that are going on. We can't take the gradient. But if we can, these methods tend to be quite powerful. And again, like I said, it's kind of insane how they can just train these like machine learning models with millions and millions of parameters. Okay, but if we can't take the gradient, we're not totally stuck here. We can actually use something called zero order methods, or sometimes they're called direct methods. And they basically do this descent just based on function evaluation. So all you have to be able to do is take an input and get the objective value output. You don't need to know what happens in between. So you might have heard of Hooke-Jeeves or Nelder-Mead. These are very common direct methods. And what's cool about them is they can work for black box systems. So even if you have kind of just this big, crazy simulator, you don't know how it works, as long as you can give it your input state and disturbances and get out a trajectory such that you could evaluate the objective, you could actually use these methods to find failures of these systems. Okay, so let's look at what local descent methods look like. So here's going to be an example of gradient descent. And we're looking at the pendulum again, where each of these dots represents a disturbance. And the way we've initialized it, you remember we need some sort of initial guess here. So we've just said that we start at an initial state of 0, and all of our disturbances are also 0, so the pendulum just kind of stays completely vertical the whole time. And then you'll see we could take a step here. So if you noticed, even if you blinked, maybe you didn't, but there's kind of a tiny step that occurred here, where we just kind of perturbed these disturbances ever so slightly to try to move that trajectory towards a failure. And then as we continue to kind of take more steps, you can see we slowly perturb it and select these disturbances to a point where we can cause the pendulum to fail. So that's local descent, and then kind of to contrast that with population methods, in this case, we're now maintaining a full population of possible samples, so we're maintaining a whole bunch of different trajectories for the pendulum. And then now every time we take a step, we update all the samples in that population to try to move them towards failure. And then over time, we get to a point where we can kind of find multiple failures of the system. And what's kind of cool about population methods is you'll remember in the previous, in local descent, when we just did gradient descent, it kind of just perturbed the trajectory until it just went off to one side. So we just found one failure mode. But what's kind of cool about population methods is they kind of encourage the population to spread out amongst all of these different possible minima. And so we're actually able to find failures in both failure modes for the inverted pendulum when we use methods like this.
Quick question.
Yeah.
So when you say we take a step, you mean like an optimization step in that case?
Yeah, good question. The question was, when I take a step, do I mean optimization step? So yeah, I can see how that'd be getting confused with like the step that we talk about in this class. I mean, yeah, a step of the optimization algorithm.
Okay, and in that case, the optimum will be kind of with respect to, well, I mean, we have this cost function we define that trades off your robustness and your likelihood, right? And so the optimum, or kind of the picture that you showed, we don't just have all failure cases because we also want them to be kind of likely.
Yeah. So the question was like, so we're not just going to have all possible failure cases because we want them to be likely, so we're just going to be finding the likely ones. That is true. I'm actually not sure what objective I used for that example. I might have just been using robustness, but if you were using that objective, that's true. All right, so that is a super brief overview of the huge field of optimization. If you want to know more about it, so for this class, that should be sufficient. I just want you to like kind of understand the trade-offs between these methods so that you can go to these off-the-shelf tools and plug them in to do this falsification for you, and mainly understanding kind of that black box versus needing gradients type of thing. But it is a really interesting field and super, super useful to know things about. So I would recommend this class if you haven't taken it yet. Next quarter, taught by Mykel, and he'll dive into these in much, much more detail. So would definitely recommend. Okay, so yeah, just to kind of recap here, we talked about how to kind of systematically search for failures, and I introduced fuzzing, which is, like I said, where I would start with for project 1. And then I talked about kind of this optimization, which can help us kind of more systematically try to optimize these objectives to find failures. And that's what I would do if I wanted to improve my leaderboard score on project 1. Any questions on this lecture? Yep.
Doing like local descent methods is just like one sample at a time. Like I don't really understand what it is.
Yeah, so the question's like, can I explain population methods a little bit more? Like, what's the difference between that and just kind of maintaining one sample and moving it? So I think the idea is kind of like, if we go back here, whoops, wait a minute. So with local descent, we just kind of take one sample and we try to move it. With with population methods, what we can do here is now we've kind of just sampled all over our possible space of, in this case, like just X, but in general, it would be like a bunch of different trajectories. And so that allows us to kind of get a more global view of what's going on. And then we can take all of those samples, and now some of them will end up in this minima, some of them will end up here, some of them will end up here. And so it's kind of a way to avoid just ending up in like one local minima. Yeah.
So each X, like each starting sample, is a whole trajectory, not just the initial space that we're starting from. It's the whole trajectory.
Yeah, exactly. So the question was each X is like a whole trajectory. Yeah, so here I'm just showing it in 1D so we can actually like visualize it. But in general, like we're searching over this kind of big space that can be like, 50 dimensional or something like that. It's a full trajectory. Okay. So let's go to the next lecture. Everything we just talked about was doing falsification. For this next lecture, we're also going to talk about falsification, but we're going to come at it from a slightly different perspective. So before we were using optimization, and we were also doing lots of setup with like these disturbances and whatnot. And now we're going to do falsification through planning. Okay, so I'm going to introduce this topic with a little bit of a story. So the question is, why do we save our work periodically? This is kind of a rhetorical question, but basically, you can probably imagine where this story is going. So over the holidays, quite recently, me and my husband were like visiting family, and he didn't have very many days off work, so he had to work remotely for a lot of our trip. And so we were both kind of working remotely from my dad's kitchen, and we were like getting ready to wrap up for the day and go grab dinner with my dad. And all of a sudden I heard some commotion coming from his side of the kitchen. And I looked up and I was like, what's going on? And he was like, my computer just crashed and like I lost everything and oh my gosh, and like I can't go to dinner now and blah, blah. And I was like, oh, like, let's try to get it like turned back on. Like, when was the last time you saved? And his reply, 3 hours ago. So I like to think that I'm normally a very kind and caring wife. But in that moment, something just came over me and I was like, you haven't saved in 3 hours? Like, that's on you. For the record, wrong thing to say when someone has just lost 3 hours of work. So anyway, then I switched back to kind and caring wife and was like, okay, well, we'll get this figured out. You can do this after dinner. We'll get it all redone. It's okay. But it kind of gets me thinking like, okay, why do we save our work periodically? I don't know, because like I'm just like Control S like every 5 seconds. So it's very different from this 3 hour cadence that he was on. And I think the reason we save our work periodically is because, rather than just kind of at the beginning and the end, is because we want to be able to go back to the point that we were at before. So we don't want to have to kind of build everything up all at once, and if something bad were to happen, like for example, we don't like the direction we were going or our entire computer crashes, we can just go back to the point that we were at before. And so kind of the idea of this lecture is that maybe sometimes it's kind of easier to iteratively build something up than to do it all at once. So that's what we're going to talk about with these like planning algorithms. And if you remember from last lecture, which we were just talking about, so it should be quite fresh, we had this optimization problem where we were minimizing over the entire space of initial states and the disturbances at every single time step in the trajectory. And we can just rewrite this optimization problem. So we have like tau equals rollout. We could just replace the tau with the rollout. So I'm just going to rewrite it like that. And so this kind of optimization problem, it typically involves searching over a very high dimensional space, as we've already mentioned a few times. So for example, for the inverted pendulum, we have our initial state, which is 2-dimensional, and then each of our disturbances is 2-dimensional, but we have one for every single time step. So this kind of sequence of disturbances is going to be 2 times d dimensional. So for example, if we had a depth of 21, which is actually even smaller than the depth that we had been looking at, we were looking at 41 before, the search space is going to be 44 dimensional. So this is already pretty big, and that's not even a huge problem. So For these bigger problems that have like even bigger states or bigger disturbances, it could be hundreds of dimensions that we're trying to search over. And that's kind of a lot to do all at once. And so what planning algorithms allow us to do is to basically iteratively build up this trajectory instead. Okay, so for the plan for today, we're going to talk about kind of a category of methods for quite a bit of the lecture called tree search. And one of the really cool contributions, I think, of the book we created is that we unified quite a bit of different types of tree search that are out there into just 2 steps. So we're going to talk about that framework. Then we'll talk about some specific implementations of that. So we'll talk about one called heuristic search. We'll talk about Monte Carlo tree search, a little bit about reinforcement learning, and a little bit about some requirements for the simulator that you're using if you want to use these methods. Okay. But let's get started with tree search. Here's a tree that's searching for its groove. For those of you who haven't seen this before, this is Mykel. He got to live out his lifelong dream of dressing as the Stanford tree. All right. All right, so we're not really talking about that type of tree, although it's quite fun. We're talking about this type of tree in this lecture. Okay, so the kind of structure of the trees that we're going to be looking at for this lecture is every single node in the tree is going to be some state for our system, and then every transition or every edge represents a transition between the nodes. So to get from this state, we had this disturbance, which resulted in observation O, action A, and then eventually the next state, S. Any questions on that structure? Yeah.
Sorry, to clarify, the letter X is used a lot since disturbance and also here. Can you clarify what exactly the letter X is?
Yeah, we typically use it to mean disturbance. So the question was, can you clarify what the letter X is? Here it's meaning disturbance, for sure. Sometimes if we're just talking about like general optimization or like a very general variable, we also use X, so I can see the confusion there. But here it's disturbance. Okay, so an example that we're going to use quite a bit throughout this lecture is, we call it the continuum world. It's in the back of the book. But the general idea here is it's kind of a continuous version of a grid world problem. So we have an agent that can move around within this space, and it needs to reach this goal while avoiding this obstacle. And it can take actions of, similar to the grid world, it can take actions of like up, down, left, and right, and it will move 1 unit in all of those directions. But again, like the grid world, it's slippery. But now instead of slipping exactly in one of the cardinal directions, it can just, if it says it's going to move up, it might just slip a little bit at some angle that's kind of close to up, but not quite up. And so our disturbances in this case are just the things that cause it to kind of slip and how much it slips, basically. And so we could look at what a tree might look like for this continuum world. So here, each node in the tree is a different state. So we're actually showing the nodes where the states actually are. So this node represents this exact position in the continuum world. And then the edges are possible transitions between states. So for example, at the root node, one disturbance would take us to this state, and another disturbance would take us to this state. Okay. And so now that we kind of have a concrete problem, let's talk about what a typical iteration of a tree search algorithm might look like. So what we do is we have kind of our current tree that we've maintained. And the first thing that we do is we select a node that we want to focus on. So for example, we select this one. In a bit, I'll talk about how we actually select this, but this is just the first step. And then once we've selected a node, we do something called the extend step, where we extend it. And all that's going on here is we sample a new disturbance, which gives us a new observation action and brings us to a different state. So to kind of summarize here, we have basically 2 steps in a tree search algorithm. One is the select step, where we select one of the nodes that's currently in the tree to extend, and then the other is the extend step, where we actually extend it. So I haven't talked about how these work. And in fact, though, with just these 2 steps, we can create kind of a general algorithm for tree search that's going to allow us to unify all of these different types of tree search we're going to talk about. So all that's going on here is we initialize our tree in some way, and then every single step of the algorithm, we select a node, and then we extend it. And all of the algorithms that we're going to talk about just differ in how they actually go about implementing this select and extend step. So how do they decide which node to select, and then how do they select a disturbance to extend it? Yeah.
I'm confused. What is like S here? Is it like the state I want time step in a rollout, or is it the initial state or something?
Yeah, so the question was, what is S? So it's each of these S is like a different possible state. So the root node would be like the initial state, and then all of these other S's are like states you could reach from there.
Okay, so it's like a depth D, we have like the entire like rollout.
Yeah, so like here would be like a depth of 3. Yeah. Okay, so that's tree search, and now we're just going to talk about all of these different ways we can implement those select and extend steps. So the first type of search we're going to talk about is heuristic search. And no surprise, heuristic search uses heuristic search algorithms use heuristics to explore the space of possible trajectories. Another name you might have heard this go by is rapidly exploring random trees, or RRT. That's kind of another name for the algorithms we're going to be talking about. So the way that RRT works is, again, we have to implement these 2 steps, select and extend. So starting with the select step, the first thing that we do is we sample a goal state. So we just sample some state from our state space. That's the goal that we're trying to get to. Then we compute some sort of objective for each node in the current tree. So each of those states that we have in our current tree, we compute some sort of objective. I haven't told you what that objective is yet, but we compute it based on the goal state. And then we'll select the node with the lowest objective. I'll do an example in a second. Once we've selected a node, that's the node that we want to extend. And so to extend it, we just select a disturbance. We take a step from the selected node using that selected disturbance, and then add the result to the tree. And then we can just keep repeating this process to kind of build up the tree. So let me show an example to kind of make this concrete. So with our continuum world, we'll start with our select step. So let's say this is the current tree that we have. And the first thing we do is sample a goal state. So kind of the vanilla version of RRT, the kind of simplest thing you could do is you could just take your entire state space and sample a random state from it and just say that's your goal state. So here's our goal state, it's this yellow star. And then we compute some sort of objective for each node in the tree based on the goal state. So one very simple objective we could use here, for example, is just like the distance to the goal. So we can look at this goal and compute its distance to each node in the tree. And then all we're going to do is select the node with the lowest objective value. So in this case, we're selecting the node that's closest to this goal state. Okay, so that's the node that we've selected to extend, and now we need to extend it. So one really simple thing we can do is just sample a random disturbance. So in this node, our agent wants to go up, and so a disturbance is going to be like some slipping with respect to this action to go up. And so we'll just sample a random disturbance, so we just slip a little bit to the right. And then we take a step following that disturbance and add the result to the tree, and then we just start over again. Question?
Are we trying to choose a less objective?
Sort of. So the question was, are we trying to choose the lowest objective because we're trying to make it fail? In a second, I'm going to show an extension where that's the case, because what we're doing right now is a little bit silly. Because right now, we're just sampling a goal state like uniformly from in here. So we're choosing the lowest objective to try to get it to the goal state. So whatever goal state, let me see if I can go back here. Like whatever goal state we had sampled, we're choosing an objective that should hopefully move it towards this goal state.
The lowest objective just means closer to this goal state.
To the goal state. Yeah, exactly.
Another question. I guess it looks like at least like the way that this RT is like set up, you don't make new nodes at the end of this. So you're only looking at nodes that you've extended further, one of the very initial ones. I guess would you not be able to explore this because you're only extending rather than like because you're probably only going to extend the one that's like closest to the thing, right? So you're never adding new nodes to explore after.
Yeah, so the question was, how are you ever going to like extend and really explore the space? Because you're only going to extend the ones that are closest to the goal state. Well, so in this case, we just sampled a random goal state, so it happened to be here. But if we had sampled a goal state that, for example, was like right here, we would end up selecting the root node to extend. And so then we would extend this node. So we can actually we'll end up extending kind of like we could extend any of these nodes depending on where the goal state got sampled.
It's like generally the nodes, there's like additional nodes that pop up at the place of your path. Usually, right? Or that's, I guess maybe.
Like in the extend step, do you mean?
Yeah. So I guess like when we extended it, usually, isn't it that there's like additional nodes that kind of pop up from that?
Yeah. So when we extended this node popped up.
Yeah, and then like usually doesn't it start from there? It's so true.
No. So the question was, does it start from here now? Do we like just decide this node is like the next one we're going to do? No. So we repeat this process. So this is our new tree. We're going to go back to the select step. We're going to sample a goal state, and we're going to now consider all of these nodes and decide which one we want to extend next. Yeah.
Can you make some normative statements about what we want the objective to look like and what the goal state to be?
In general, you mean?
Sorry?
Like in general? Like,
Yeah, like what are, like, make some normative statements about, like, what's the point? Like,
Yeah.
what are these things?
What is the point? Good question. So the goal state, I'm going to show in a second, like, be kind of nice if our goal state was right here, right? Because we're trying to find a failure. So that's where we're heading here. But in general for RRT, just if your goal is to kind of just explore the space as much as possible, you want to sample your goal state from all over the place, anywhere in your state space. But then for computing the objective, your goal state is now the new goal that you're trying to get to. And so your objective should be something such that the node you extend will get you close to that goal.
So why isn't something like Euclidean distance always
Well, sometimes we're not in a scenario where it's like a continuum world, and like Euclidean distance might not have like an actual meaning. Yeah. In this case, Euclidean distance typically makes sense. Any other questions?
So what we're going to do is that we're going to like be in the S comma X dimensional space, and then with the like objective function being like the one that we discussed earlier for classic tree. We're going to do that somehow.
We will get to objective functions in a second. So right now we're not really assuming there's any objective other than finding a failure. And really with rapidly exploring random trees, the way I've presented it right now, the objective we're kind of optimizing is just like explore the space of possible trajectories for the most part. And we're just hoping that we might stumble upon a failure. So just along that note, here's what the algorithm might look like, starting from the beginning. So at every iteration, you're going to see us sample a goal state and extend the tree outward towards that goal state. But the goal state gets sampled from a whole bunch of different places, and so we kind of extend different nodes and build out this tree. Okay, so here's what it looked like. I think this was like 100 or so iterations. But you might be thinking, okay, so we did kind of explore the space. You look like you're deciding.
Why we got so lucky as to always not hit the red and always hit the green. Like we sort of are trending towards the green and also not hitting the red.
Yeah, that's a good
Random
observation.
sampling should not emerge, right?
Yeah, so it seems like this is random, but what's going on is when I sampled, maybe I didn't fully explain this, so when we select the disturbance, I'm sampling from the nominal disturbance distribution.
Oh.
So when we want to go up here, we're more likely to get disturbances that actually do lead us up. So we're going to end up getting trajectories or a tree that kind of moves in the way that we expect the system to with these randomly sampled disturbances.
The system has already learned, like the system is already trying to get to green.
Yeah, the system is trained to try to get to green, and we're trying to find scenarios where it might get to the red. Yeah. But so we did kind of explore the space, but this didn't quite work because we didn't actually find any failures. So like I said, we were just kind of trying to explore the space as much as possible, the space of possible trajectories, and in hopes that we might find a failure, but we didn't. So one thing we could do is we could just run this for longer and hope that we do find a failure. But we could probably be a little bit smarter about this, and instead we'll just try to make some improvements to our algorithm. So we already kind of alluded to one improvement, and that's in the select step. So before we were just kind of sampling from the entire space of possible states at every single iteration in order to sample our goal. So we could just get a goal kind of anywhere, but we kind of know what our goal is. Like we're trying to find a failure. So why not just sample states from the goal state, or from the failure region sample goal states from the failure region every single time rather than this entire space. So that's kind of one improvement that we can very quickly make. And so we'll just say instead of sampling goal states from all over, we'll just always sample a goal state in the failure region. Why didn't we just do this off the bat? Well, it is the case that not all systems have an easily identifiable failure region. So like I said, like, you know, Euclidean distance makes sense here. This continuum world's like a really nice problem to demonstrate all of these things on. But in other scenarios, it might not be so obvious, like what is the region of states that represent a failure? Especially when there's like temporal properties involved, you might not be able to say like, if I get to this state, it's like for sure a failure. And so we can't always do this. But in cases where we can, this can make our algorithm perform quite a bit better. And then secondly, in the extend step, so we did talk about, I was just kind of sampling a disturbance from the nominal trajectory distribution. So the only thing we were doing to kind of incorporate our goal was selecting a node that was near the goal to extend, but then we're just picking any disturbance. So we weren't really picking a disturbance to try to steer us towards the goal. So we could add that in. So let's zoom in on this kind of lower left corner here. And let's say that this, for example, is our goal, and this is the particular node that we're going to extend. What we could do is we could try to sample the disturbance that would get us as close as we possibly can to this goal. So what we might do is sample, one way to do this would be to sample a whole bunch of disturbances and then pick the one that got us the closest to extend for the next step. Question? Yeah.
I guess, let me preface this. So were we trying to find pathways that were most likely to get from, or most likely type of failures to happen? Isn't that the...
Great question. So the question was, weren't we trying to find the most likely failure? In the previous lecture, when we were doing the optimization, that was an option for the objective, and that's generally a good objective to use. That's typically what we want to find. What I've presented so far is not using that objective, but in a little bit, we're going to talk about how we actually could. Any other questions on this? Yep.
This doesn't generally, this isn't generally the most likely failure trajectory. We're just trying to manipulate our searches so that they're constrained to like minimize the overall space that we have to look over.
Yeah, so you can think of our objective right now as just, we're just trying to find any failure that we possibly can. Yeah.
So for the disturbance, are we sort of always selecting disturbances that, like, we measure a distance to the goal state and we literally just kind of go there?
For this particular case, yeah, we would just, well, so really what our goal is to pick the disturbance that would get us closest to the goal state of all possible disturbances we could choose from. One way to do that is to sample a bunch of disturbances and pick the one that gets us the closest. We could try some fancier like optimization to actually try to find that disturbance.
Okay, but in this case, we're simply just sampling a counting basically.
Yep, exactly. Great. And you can imagine like the more samples we take, more computational expense, but the better we'll get here. So there's that trade-off. Yeah. Cool, so now we've made those two modifications and you can see the algorithm runs much more efficiently, and we're able to find a failure, and we're able to find it pretty quickly. Okay, we found a failure. So that's two very common extensions, very easy things to tweak to kind of make the algorithm run a little bit better. There's a few other common heuristics that people use. One is coverage metrics. So we actually alluded to these a little bit in the last class when we were talking about like how do we know when to stop. And so one thing you might want to do when you're kind of making these random trees is you might want to explore the space of possible trajectories like truly as much as possible. And so one thing you could do is actually use coverage metrics to guide the search. So you could, in this case, your objective is kind of like explore the space as much as possible. And there's these metrics called dispersion, and I think we talk about another one called star discrepancy in the book that allow you to kind of understand how well you've covered the space of possible states, and then use that to kind of select the next node to extend or to do the extend step. And then, for example, when we use coverage metrics like this, we have some sort of, we can kind of measure the growth of this coverage over time. So here we're plotting, for example, as we run the tree search algorithm, the result of some coverage metric over time. And you can see it kind of starts to plateau at the end here. And so you can imagine when our coverage isn't growing much anymore, our tree is not really changing much anymore. And so we can say, like, maybe that's a good time to terminate the tree search algorithm. So there's no guarantees here. There still might be, you know, spaces we haven't explored or haven't found, but this is kind of one way that we could kind of make that decision. Unfortunately, we don't really have time to actually dig into these for this iteration of the class anyway, but if you're interested, it's all in the book. We have nice implementations of these things, and I think it's a really cool topic, so definitely check it out if you're interested. The second common heuristic, which I think a lot of you have already been asking about, we're going to dive into, which is alternative objectives. So before we were just kind of trying to explore the space. Now can we actually incorporate those objectives we had last time where we wanted to find like the most likely failure, or for example, maybe we want to find like the shortest path to a failure. How do we go about incorporating those? Okay. And so the way that we do this, kind of maybe no surprise, is we can incorporate alternative objectives when we do that kind of compute objective step in the select step. So if you remember, we had the select step and we had, you know, some goal state, and then we were computing an objective for each node in the tree based on this goal state. We can kind of change how we compute this objective in order to incorporate alternative objectives. Okay, so from before, for example, we had this goal state here, maybe in the failure region, and when we were deciding to extend this particular node, we realized that it was just the closest to this possible, or to this goal state. And now what we're going to do instead is we're going to specify this cost function. And the cost function consists of two things. So the first thing that it consists of is something that we'll call the current cost. And that's basically the cost it required to get to the node that we're currently at. So it's like this kind of cost that we have so far to get here. And then the second part of the cost function is kind of the cost to go. But there's one problem with this objective, or with this part of the cost function, which is that we don't really know the cost to go. Like maybe the path goes like this to get there, and maybe the path goes like this to get there. Like we don't really know what's left. Because if we knew what was left, we would have already solved the problem because we'd already know how to get to where we're trying to go. And so that's kind of the issue. We don't know this. And so what we typically do is instead we try to estimate it using some heuristic function that we'll call h. So for example, in this case, one heuristic function we might use is just kind of the Euclidean distance between our current state and the goal state. And that's kind of our cost to go. So for example, if we now want to find the shortest path to failure, our current cost would just be the distance to the current node in the tree, so this pink part here. And then our cost to go would maybe just be kind of the distance to the goal as the crow flies. So just whatever the most direct path to the goal is, what is that distance? And we'll add those together. So then we would compute this for all of our different nodes in the tree, and then pick the smallest one to extend next. So looking at this, it's a little bit hard to tell, but does anyone have any guesses of which one we would extend next? I heard 6, yeah.
Number 6.
Number 6? Yeah, number 6. So it's kind of hard to tell, but this is like, if we add the pink and the purple, the 6 will be the lowest one. So, because you can imagine one looks like it's kind of close, but it kind of had to go back and forth like this. So we would actually extend number 6 next based on this cost function. Okay, so that was if we want the shortest path to failure. But now, as many of you have been wanting to know, how do we find the most likely failure? So for most likely failure, our current cost is just going to be the negative log likelihood of the trajectory so far. So remember, we need a cost, something that we want to minimize. So we need the negative log likelihood for this. And one note here is that costs must be positive to ensure that the search will terminate. So if costs were negative and we're trying to minimize cost, then we could just kind of go in circles forever, kind of like that boat was in that one game we saw. We could just go in circles forever and continue to minimize our cost. So we need to make sure that costs are positive so that we will actually like encourage the search to terminate. But the problem here is that like negative log likelihood might in fact be negative. And so we kind of have this issue where we need to make sure that this is positive. So we just add on some constant, typically maybe like the highest log likelihood you could have, so that all of them will be positive. You just need to basically make sure that you're never going to have any negative costs. Okay, and then finally, the cost to go is we're going to need some way to basically estimate the negative log likelihood that we have left. So there's various ways to do this. There's no kind of super straightforward, obvious way. But one thing you could do is you could just say like, well, the distance to goal is a proxy for this negative log likelihood, because shorter paths tend to have higher likelihood, just because, you know, it's probably unlikely that it's kind of going around all over like this and then gets to the goal, and this is going to be a more likely path. So that's, again, this is just a heuristic, so it's just something we're using to help kind of guide the search. So it's not an issue if it's totally wrong, but we just need something that's kind of close. Any questions on this? Yeah.
I'm still confused about this, the requirement for this plus C, since I would think the negative log likelihood is it unbounded in the minus direction?
I guess it depends on what distribution you're sampling from. So in a lot of cases, you know kind of the bounds for it.
I guess I'm a bit confused because the concern is that we might find like a loop in our trajectories which minimizes our cost. But I think since our cost is, we're trying to maximize our likelihood by minimizing our cost, there must be a lower bound, right? Because our likelihood can't be, or I guess our probability can't be higher than 1.
Yeah, well, probability density can be higher than 1, because the probability density is not an actual like probability. But if you know, for example, like I'm sampling from a Gaussian distribution for my disturbances, then you can get a bound on like how big the log likelihood could get, how big that density could get, and then you could just like add on a constant to make sure that you're always going to be positive. Yeah, I wouldn't worry too much about the details here. If you were actually going about implementing this, which we did for some of the figures in the book, that's where we discovered this issue, and it's basically just, you just need to kind of bump it up to make sure that your search will terminate. Cool. So here's kind of what it looks like with both of these different cost functions. So we talked about shortest path to failure. When we run this, we'll get a path that kind of just goes directly to the obstacle. But this might not be super likely because we're going to sample a bunch of disturbances that are kind of maybe quite large. They're not very likely to happen. And then kind of what's shown here also in white is the nominal path that the agent would take if we had no disturbances at all. And then if we look at what's the result of finding the most likely failure using this method, we get something that stays much closer to the nominal path and just kind of deviates at the end and falls into the obstacle. Yep.
We would estimate the negative log likelihood of the places to go, since it's like since we haven't actually gone there yet.
Yeah.
But is it just that we have like a general sense of the cost for every single path to get there?
Yeah. So the question is like, can I go over again how we estimate the negative log likelihood to go? So it's kind of difficult to get right. So you know, if you're this far away from the obstacle, one thing you could do is just say like, okay, I'm this distance away, and you can kind of use distance almost as a proxy for likelihood, because the more time steps that you're kind of moving around, the more time steps you're accumulating these samples of disturbances, and so the lower your likelihood is going to be. And so you can kind of say ones that are closer to the goal will have a lower log likelihood to go. And that's just a proxy. There's other ways that you could try to estimate it. Like, for example, you could do a whole bunch of rollouts and try to look at the log likelihood of those rollouts and look at what was to go. Yeah.
I guess the question then is like, what's the difference between,
Because we use distance as a heuristic for the shortest path to failure. So like, why can we use distance again for the likelihood?
So again, these are kind of just heuristics to guide the search. So it might not perform as well as if we could actually, like, it's probably a better proxy here because these two things match. Here, it might not perform as well, but we're using it as a proxy for this one as well. But for the current cost, we can actually use the negative log likelihood, so that'll make it different.
Yeah, maybe this is the part where you would take advantage of any kind of domain expertise. Many domains don't have a natural definition of distance even.
Just to repeat that, Mykel was noting that in this case, or in lots of cases, like we would just need to use domain expertise to design all of these various heuristics, because sometimes like distance isn't even like an obvious thing or something that we would talk about in a particular domain. Everything's just very clear in this continuum world, which is why we used it as an example. But in general, this might not always be so obvious. Good questions. All right. Okay. So just one more note on all of this. It turns out that if the heuristic is something that we call admissible, and the state space and the disturbance space are both discrete, then this algorithm turns into A-star search, which is kind of cool. So some of you may have heard of A-star. What does it mean for a heuristic to be admissible? It's admissible if it's guaranteed to never overestimate the cost of reaching the goal state. So again, kind of like Mykel was saying, this takes domain knowledge to design, and it's not always easy to design a heuristic for which this property is true. But let's look at the grid world example now, because we need our state and disturbance space to be discrete. So we're going to switch to a discrete problem here. And we can think about what an admissible heuristic might look like here. So let's imagine that this is the node that we need to estimate the cost to go for. A very common admissible heuristic to use is kind of this distance as the crow flies, so the Euclidean distance between the state we're at and the state that we're trying to get to. And the reason that we know that this is admissible is because it will never be greater than the actual cost of reaching the goal state. So we know from here, we can't actually do this because in the grid world, we're only allowed to move in kind of these discrete directions between cells. So the shortest path is actually going to be like that. And so we know that this, by the laws of triangles, is always going to be smaller. And so similarly, this is the case from like any state that we encounter. And so the Euclidean distance is an admissible heuristic here. And then this turns into the A-star search algorithm, which means that we're guaranteed to find the optimal path. So in RRT, we were just kind of encouraging it to. We were hoping to find these good paths to failure. There was no guarantees involved there. When we have kind of these specific conditions, we're actually able to guarantee that we'll find the shortest path or the most likely failure. So here's what that looks like for the grid world. The shortest path just kind of goes right to the obstacle, and then the most likely failure stays along the nominal path until it kind of dips down at the very end. Yeah.
Intuitive reason to kind of understand like the why it shouldn't overestimate the cost of reaching the goal state.
Okay, hopefully I'm not going to butcher this answer because it's been a while since I've looked at A-star. But so the question was, is there an intuitive reason for like why it can't overestimate it? Typically when you're doing A-star search, you like prioritize certain nodes on top of others, and you need to make sure that it's going to be like prioritized in the right order. Did I say that right?
You get a guarantee of sounding completeness if it's admissible.
Yeah, but like the intuition for why that's the case. Yeah, okay. So it's kind of that. I would recommend, we're not really going to get into it in this class, but I would recommend checking out like, there's some really nice YouTube videos on like A-star search. And I think it'll become like pretty clear why all this fits together. This is kind of funny because I honestly didn't think we'd get this far. And so when I was looking through my slides last night, I only went up to here. And then I told my husband if we got this far, I was going to be doing slideshow karaoke, which is when you have a slideshow and you don't know what's coming next. So here we go. All right. Now we're going to talk about something called Monte Carlo tree search. So we try to balance. So what's cool about Monte Carlo tree search, kind of beyond RRT, is that we have kind of this explicit way to balance between exploration and exploitation. So the idea here is like, we want to explore the space of possible trajectories, but we also know that after we do some exploration, we know that there's some trajectories that are more likely to lead us to failure, and so we want to also be able to exploit that knowledge. And we'll do this by determining promising paths by maintaining a value estimate for each node in the tree, and we're going to call this value estimate Q. And just to kind of avoid any confusion off the bat, in other classes, for example, if you took AA228, we're often trying to maximize our value just to keep it consistent with all the costs that we've been talking about so far. In this case, we're going to actually want to minimize Q just for this class. Okay, and so what's really cool is we showed that we can actually just kind of frame Monte Carlo tree search in the same way that we framed these other algorithms, where you have a select step and you have an extend step. And in the select step, at a high level, what's going on is we want to select a node that we currently have in the tree to extend based on a heuristic that balances between exploration and exploitation. So that's where that part kind of comes in. And then when we get to the extend part, we sample a disturbance, add it to the tree, and propagate the results back up. So I'll show you what that means exactly. So again, we're going to assume that we've had some tree so far that we're starting with, and let's talk about what we do for each of these steps. So first, we'll start with the select step. And in Monte Carlo tree search, like I said, we maintain this value function for every node in the tree, or value estimate for every node in the tree. So that's what this Q is. Every single node has some Q associated with it. And again, we want lower values mean that they're better. So for example, just to kind of give you some intuition, this node is pretty close to the failure, so it has a pretty low value. The other thing that we maintain for each node in the tree is this count n, which is just the number of times that we've visited that node in our tree search. So we're assuming that already the tree search has been going on for a little bit, and so we have some n's and some q's from these nodes. And now we want to do one more iteration of Monte Carlo tree search. And so the first thing we do is this select step. And the way it works is I want you to kind of imagine that you're in this space here and you're going to walk along this tree. And we're going to start at the root node. And for every select step, the first thing that we do is we look and see if the number of children of the current root node is less than or equal to this value here, where n is the number of times we visited the node that we're currently at, and k and alpha are some hyperparameters. So alpha should be between 0 and 1, but in general you can kind of just select these and they'll kind of control the trade-off between how much we will end up extending or sampling new things from this node versus going kind of deeper in the tree. And then if it is the case that the number of children is less than this number, then that means we want more children for this node. And so we're going to say yes, and we would select it and move to the extend step. If not, we move to the child node that minimizes this. So I'm going to get into what's going on here in a second, but just know that if yes, we're going to extend it, go over to the extend step. If no, we're going to start traversing this tree. Okay, so let's talk about actually what's going on if we do want to traverse the tree. And this is where we actually balance between exploration and exploitation. So we're at some spot and we're going to look at all of the places we could go by looking at all of the child nodes that we have. And we're going to compute this value for every single one of the children. And this value is kind of a combination of two things. The first thing is this Q child. So that's exploitation. So if the child already has, so we're going to end up picking the lowest one. So we want this value to be low if we want to pick the child. And so this exploitation is, well, if the Q is already low, then it might be a good idea to go there because we know that that's probably a promising path. But we also want to explore. So we don't always just want to exploit what we know because there might be something better out there that we don't know about. And so this term here kind of balances that. So if we haven't visited that child node very much, then this value is going to be bigger. And so we're going to get kind of a bigger, what we call exploration bonus. And that's going to tell us, well, okay, maybe the Q is not so good, but we haven't been there very much, so let's go explore that node. And the way we kind of control the trade-off between these two things is with this thing we call the exploration bonus. And that allows us to kind of trade off between this exploration and exploitation depending on what we want to do. Was there any questions on that? Yeah.
Is the n in the numerator the same as the n in the denominator?
Oh, so let's go back here. So the n in the numerator is the number of times you visited the node that you're currently at, and now you're looking at the children to decide what to go to, and so the n in the denominator is the number of times you visited that child you're deciding if you want to go visit. Okay. So let's do an example here. So let's imagine that, for example, k is equal to 1 and alpha is equal to 0.5 for these parameters here. I just picked these to make the problem work out. So now if we plug in n here, we get 2.82. So is the number of children, which is 3, less than 2.82? No. So we're going to follow this path over here. And so now we need to look at each child node, and we're going to compute this value for each child node to decide which one we want to move to next. So, for example, for this child node, we'll just plug in our q child and our n's, and we get 9.26. For this one, we get 0.78. And for this one, we get 11.26. And so we're going to move to the one with the lowest. And so one other thing I forgot to mention, this is sometimes called a lower confidence bound. Maybe you've seen the opposite in AA228, where we have a plus here because Q is, we want Q to be higher in AA228. In that case, it's called an upper confidence bound. Okay, so we're going to pick the one that's the lowest here, so that's this one. And then we're going to just move to that node and repeat this process. And so now we'll repeat this process again, so we can say k equals 1, alpha equals 0.5. Let's compute this term here. We get 1. The number of, I don't think we get 1. We get 2. Maybe that didn't update. But we get 2 here, because the square root of, oh wait. Yeah, I didn't update these numbers, but we should get 2. I'll fix that in the slides later. So we get 2 because I wanted to stop at this node. And so this inequality is satisfied. And so we're going to select this node and move on to the extend step. Ignore these numbers; they don't add up. Any questions there? Yeah.
I'm a little confused by like the k and alpha. Like I guess like where does that come from?
It's kind of just a heuristic people use to decide like. So basically, when you're at a node, you have a bunch of children. You can decide whether you want to extend that node or just go deeper in the tree. And you can imagine that if you have a ton of children, then you probably don't need to sample more of them. And so you probably want to go deeper in the tree. And this basically balances between, it kind of like balances that objective. So it allows you to say like, if I have more children, then I probably just want to go to one of them. I don't, which would mean that we follow like this step where we go traverse the tree further. But if I have enough children, or if I have not enough children, then I would want to go to the extend step at that particular node. Does that make sense? And k and alpha are just parameters you pick that will kind of control how many children you end up with. Yeah.
Is this like condition here to like handle the continuous world that we have? Because I remember in 228, we just started with the MCTS, and there was no checking how many children each node had.
Yes, good question. So you have to do this when there's not a discrete number of outcomes that you could have when you're switching from one node to another. So because we're in a continuous case, kind of like you said with the continuum world, we could just sample children forever and ever and ever and ever because every disturbance is going to be different because it's like a continuous space of possible things that could happen. And so we need to kind of control then how many children we have by doing this. So in other versions of MCTS, where things are discrete, you don't have to worry about this. Yeah.
Is there a step in which we use like back propagating at some point? Or?
Yeah.
Oh, okay, got it.
And then this is progressive widening.
Yes, this is called progressive widening.
Yes.
So earlier when it was like there's not enough children, and so we were on the no arrow, and then we choose the child that minimizes that score. When we choose the child that minimizes that score, do we step to that child and then we like start the algorithm again from that child, or you go back to the?
Yeah. So we were here, and then we said, we have enough children, we're gonna move on. And then we chose to move here, and now we're here, and we're doing this whole decision all over again. But I messed up the numbers, so there. Yeah. Like, if k equals 1 and alpha equals 0.5, then we're gonna get 1 times n equals 4 to the 0.5, so 1 times the square root of 4, which is 2. And then the number of children is 2, and it is the case that 2 is less than or equal to 2, so we would move to here. And I had updated these, but I guess it didn't save or something.
No, that makes sense.
Yeah, maybe save your work, guys. Okay. Did you have a question? Or? Okay. Anything else? Yep.
Yeah. N is the number of times that you visited the node. Is that correct? Oh, wait, what's Q one more time?
Q is kind of this value estimate that we're maintaining. So I'll show in a little bit how you kind of end up computing it or estimating it. But the intuition there is that a lower Q is what we want. So a lower Q would be something that's closer to a failure. Any other questions?
In a sense, it's like a cost to go.
Yes, in a sense, it's like a cost to go. Okay, so now we've decided that we're not going to propagate down the tree any further. We're going to extend this node that we're at. And so what we do is we just sample a disturbance. So maybe we sample this one, for example. We add it to the tree. And then whenever we add a new node to the tree, we need to now initialize its n and q. So n is just going to be 1. We just visited it this one time. But we need to decide what to give it for its value q. And so we need some way to kind of estimate this. And this is where you kind of have to use domain knowledge or make design decisions for this algorithm. But one thing you could do is you could, for example, just imagine doing a whole bunch of rollouts from this particular state. And then that gives us an idea of how good everything is going to be in the future from this state. And maybe you compute the robustness of these rollouts, the average robustness, something like that, some metric that kind of gives you an idea of kind of like what Mykel was saying, your cost to go. And so, for example, maybe we get q equals 3. And so now for our node, we've now added this new node to the tree with, we visited it once and we estimated its value to be 3. And then as we were asking earlier, we need to kind of propagate what we just saw back up the tree, because now we have new information about how everything goes. And so we go to the nodes that we saw before, and we say, we increase their visit count, because we've now visited them again. And then we also update their queue to be kind of this like moving average of the queue that it thought that it was, and the queue that we just found when we went to that node. So this is basically just kind of a moving average. You can look at the formula for it in the book. And then we propagate all the way back up to the root node and do the same thing. Yeah.
So, but when we define our two functions, we can, like change the parameters so like a lot more be like children, like a lot of like different roots are being created before you actually kind of like more like extend heavy than just like following. And then like, how do we optimize that? Is it, like, are we going to optimize that or like just like figure out like
yeah, so the question was like, can we make it like more extend heavy, or like how do we optimize like how far we go down the tree, that kind of stuff. So that like progressive widening step, we can choose alpha and k to kind of trade off between like how deep we go. So if we want more children, we're not going to go as deep then. And then this idea of like when we do then traverse the tree, we balance between exploration and exploitation. And that C parameter we had in the lower confidence bound allows us to kind of trade off between the two. So if we want more exploitation, we would go like deeper down the tree, deeper down the paths that are promising. If we want more exploration, we would end up like kind of going down maybe less promising paths.
I think my question is like, how do we peak C and A? Like, how do we optimize these? Yeah, that's what I mean. Like, I'm like, how do we? Because we picked some values now, but it's kind of like, is there any methodology of like, this is like the best you can do if you want to like have the maximum coverage, or like this is like what scenario you want to find?
So for K and alpha, there's like recommended parameters that people use. Is typically like 2 and 0.5, but sometimes you have to mess with it. For the exploration bonus, I think like it's probably problem dependent, because you're like depending on this Q function and stuff. So like the way you'd search any hyperparameter when you're trying to run an algorithm. So I'll try something, and you can like look at the tree that comes out and be like, hey, I feel like that's exploring more than I want it to, so I'm gonna up this value or whatever. Okay, then you just repeat this process, and let me just show you what this looks like to wrap up lecture today. This is one of my favorite figures from the entire book. So what I'm going to show here is I'm going to show kind of a run of Monte Carlo tree search to try to get to this failure. And then nodes that are visited more often, or kind of edges that are followed more often, are going to be a little bit darker than the ones that are followed less often. And so you'll be able to see kind of this balance between exploration and exploitation. Okay, pretty cool. All right, so I think Tuesday we'll continue with the rest of this lecture, and then we have a super awesome guest lecture from the other textbook author, Anthony Corso, that'll be related to all of the things that I just talked about. I'll give you some kind of more real-world applications for it.